Hey everyone, I am back and today I have two questions and one fun quiz for you. Hope you will enjoy it. Let's dive in. So here is the question number 6. So in this question it is written that a conducting sphere of radius r is placed in a uniform electric field is equals to E naught k cap. The potential at point P is given by this where r is the distance of point P from the center of the sphere and OP makes an angle with the z-axis theta. So we have to calculate the induced surface charge density on the sphere at an angle theta, and these are the options. So this is the conducting sphere, and we have placed this conducting sphere in a uniform electric field, where this uniform electric field is E naught k cap. So because of that, potential at point P is given by this. So now from this potential we have to calculate what will be the induced surface charge density on the conducting sphere. Okay. So to solve these questions, let me draw two figures. First case, I am considering that there is no conducting sphere. We have only uniform electric field. So case 1, when there is no conducting sphere, we have only uniform electric field, and one can represent uniform electric field by a set of parallel lines like this way. And let's say this is the origin and this is the z direction. So electric field in this question it is written E is equals to E naught z cap or k cap, so it will be like this direction. Now I am assuming that this is the point O, and with respect to this point at a distance r, making an angle theta with the z axis, I am considering another point P. So now if we want to write the potential at point P, well, if we want to calculate potential difference between O and P, what will be that potential difference? So one can write dV is equals to minus E dot dl, where dl is the elemental length vector and E is the electric field. Now at point O, let's say potential is V naught, and at point P, potential is V. So when we integrate this, what we'll get? We'll get V minus Vp, that is potential at point P minus potential at point O is equals to this line integral along this path. Since here is electric field is uniform, so on this path it doesn't matter where we are taking elemental length, everywhere this electric field and the dot product of this elemental length will remain same. So we can take this electric field outside from this integration, and if we integrate this dl from O to P, that will give you the length vector of this OP vector. And in this case, if this distance is r, so we can write minus E dot L vector, and the angle between E vector and L vector is here theta, so I can write minus E naught r cos theta. E naught r cos theta. And then with respect to infinity, where we assume that the electric field is zero, potential is zero, so with respect to that point, if we assume that the potential at the origin is constant, then one can write potential at point P is V is equals to some constant minus E naught r cos theta, minus E naught r cos theta. So this will be the potential at point P when there is no electric field, no conducting sphere, and we have only uniform electric field, and that electric field is not z cap. Okay, so now if we place conducting sphere in this uniform electric field, then what will going to happen? So now we'll draw the second case, so that is case 2. So in this case, we are going to place a conducting sphere in a uniform electric field. Let's say this is the uniform electric field. So as soon as we place this conducting sphere in this uniform electric field, and we know that conductor have a free electron, so this external electric field will apply a force on the free electron, and that force will be always opposite to the external electric field because electron have a negative charge. So because of that, the force, if the electric field is pointing towards left to right, then the force on the electron will be towards left. So because of that force, electron will start gathering on the left surface of this conducting sphere, and on the other hand, positive charge will start gathering right side of this conducting sphere. And this charge separations will going on until this external electric field that is given in the question, C is equals to E naught Z cap. So magnitude of this external electric field, and you can see when this charge separations will going on, there will be internal electric field which will be pointing towards the opposite to the external electric field. So until the magnitude of these two field becomes equal, this charge separation will going on, and at the equilibrium, this extra magnitude of this external electric field and this internal electric field will be equal. So inside the conducting sphere, net electric field will be 0, and at this time charge separations will look like this. So now because of this induced charge, the electric field will and no more will be parallel to each other, so they will also deform from the earlier case. So now it will look like this. Inside the conducting sphere there will be no electric field, so that's why there will be no electric field line does not exist here. And we know that electric field will be always normal to the conducting surface, so because of that the electric field line will bend like this. So now this electric field will not no more be parallel with each other. So one can represent this electric field in this presence of this conducting sphere like this. Okay, like this. And let me draw one more line here. One more line here also. Okay, so what is going to happen here? As soon as we'll place this conducting sphere in a uniform electric field, so because of this electric field, force will acting on the free electron on the conducting sphere, and because of that force, positive charge and negative charge, they will separate from each other. And finally, so if we want to write the electric field inside the conducting sphere, that electric field will be external electric field, and the electric field that will be produced because of this charge separation. So the summation of these two electric field will be 0 inside the conducting sphere at equilibrium. And now if we want to calculate electric field or potential outside the conducting sphere, so we have to consider contribution of both. One term will be associated with the external electric field, and the another term that will be appears because of this induced charge. So that's why in the questions, when the this conducting sphere is placed in the uniform electric field, let's say in this case center of the sphere is O, and this is the positive z axis. So with respect to sphere, center of the sphere, we consider this point is P at a distance r, making angle theta. So in this questions it is written potential at this point. So what that potential? That potential is written as V is equals to some constant minus E naught r cos theta, e naught r cos theta, plus I'm writing the third term in with a different color, e naught r cube divided by r square into cos theta. So in case 1, from the case 1 we can say that the first term of this given potential is associated with the external electric field, and the second term, this term, is actually associated with this induced charge. Associated with this induced charge. So I hope you understand the source of the different terms of the potential. So first two terms will be associated with the external electric field, and now since there's external electric field, there will be charge separation in the conducting sphere. So because of that, we have to, if we want to write potential at any point, we have to consider contribution of both. One part will be associated with the external electric field, and another part will appear because of the induced charge. So here first two terms of the given potential is associated with the external electric field, and third term is associated with the induced charge. So now the question says, from this potential we have to calculate what will be this surface charge density. What will be this mathematical expression of the surface charge density that we have I have shown in this figure. So to find out that charge distribution, what we have to do, we have to follow few steps of mathematics. So first we'll write potential at point P. So the potential at point P is, it is written in the question. So what is that potential? V is equals to some constant minus E naught r cos theta plus E naught capital R cube divided by r square into cos theta. So this is the potential at point P. Now what we'll do, we'll calculate the electric field associated with this potential at point P. But since this potential is function of r and theta, so we can calculate r component, theta component. But here we'll calculate only r component. So let's the r component, of electric field at point P is ER is equals to, we have to take partial derivative of this potential with respect to r with a negative sign, and then we'll put that r equals to smaller. So that will be the r component of electric field at point P. So when you will take the partial differentiation of this potential with respect to r with the negative sign, what will get? This term will give you 0. From this term we'll get E naught cos theta, and then from this term what we'll get a plus 2 E naught capital R cube divided by small r cube into cos theta. Into cos theta. So this will be the r component of electric field at r equals to r, that is point P. So now if we replace that r, keeping theta fixed, if we replace this small r by the capital R, then this P point will shift on the surface of the conducting sphere. So the r component of electric field at r equals to capital R, that is on the surface of the conducting sphere, can be written as can be written as ER at R equals to capital R. So we have this expression of ER at point P. This is now we'll replace this small r with this capital R. So what we'll get here after replacing this small r with this capital R, first term will remain as it is, cos theta E naught cos theta. Now from second term, what we'll get 2 E naught R cube divided by, we'll replace this small r capital R cube into cos theta. Okay. Now this capital R denominator numerator, they will cancel out each other. So finally we'll get the R component of electric field on the surface of the conducting sphere, and that will be 3 E naught cos theta, 3 E naught cos theta into R cap. So this is the R component of electric field associated with the potential on the surface of the conducting sphere, that is at this point. And we know one properties of the conducting sphere: if there is any electric field just outside the conductor, that electric field will be always perpendicular to the surface. So that's why we have calculated only R component, because in this case R component will be normal to the surface, and inside the electric field will be always 0. So in this case also, when you take the superposition of external electric field and internal electric field, so in net electric field inside will be 0. So we have calculated this electric field, normal component of the electric field on the surface of the conducting sphere. And now what we have to do, we have to calculate the surface charge density. So again, one can write this definition: if there is a local surface charge density on the surface is sigma, then just outside the electric field of this conducting sphere can also be written as sigma by epsilon naught. So let's write this statement here: if sigma is the local surface charge density on a conductor, then electric field just outside the conductor is written as E is equals to sigma divided by epsilon naught n cap. So in this case we have a conducting sphere, so n cap will be r cap, so we can write sigma divided by epsilon naught to r cap. Sigma divided by epsilon naught r cap. So now what we have written here, we have calculated electric field on the R component at this point. That is the normal component of electric field at this point. And also, if we assuming that the surface charge density at this point is sigma, then electric field can also be written as sigma by epsilon naught r cap. So what one can do this equal these two electric field. When you make them equal, so one can write, therefore one can write since both the electric field, this electric field and this electric field, they are representing electric field at the same point, that is surface of the conducting sphere. So one can make them equal. So one can write sigma by epsilon naught r cap is equals to 3 e naught cos theta r cap. So r cap will cancel out. So what will get sigma, which will be a function of theta in this case, and this can be written as 3 epsilon naught e naught cos theta. So this will be your final answer. So in this case, induced surface charge density on the conducting sphere will be function of theta. It will not be uniform, it will be non-uniform, it will be depends on theta. And on the z-axis it will have maximum value when theta will be 0, and it will also vary when theta will change from 0 to pi. Okay, so this is the surface charge density, induced surface charge density on the sphere. So what will be correct answer? So our correct answer will be option B. Correct option will be option B. This will be our correct answer. 3 epsilon naught e naught cos theta. Okay, so I hope you understand this. So what we have to do here to calculate surface charge density of the conducting sphere. So in presence of this uniform electric field and the conducting sphere, we have potential at point P. So from this potential, we have calculated the normal component of electric field at the surface of the conducting sphere. And if we assume that the surface charge density, induced surface charge density on the conducting sphere is sigma, so we also can write the electric field just outside the conducting surface is sigma by epsilon naught. So we'll make them equal. From there, we can write sigma is equals to 3 epsilon naught e naught cos theta. So correct answer is option B. Correct answer is option B. Okay, that is done. Now I have a quiz for you. So as we have noticed that the potential has two terms. One term is associated with the external field, and the third term was associated with the induced charge. And in this case, if you take a look on the potential on the third term, sorry, this one is square. So this term you can see that potential will be if you take the variations of potential with respect to r, what we'll see here that potential is varies as 1 by r square. That's mean this term, according to concept of multiple expansion, one can say that this term is associated with some dipole. So this term is associated with the dipole. So that's mean this induced charge in this case will behave like as a dipole, electric dipole. So now the quiz for today is what will be the dipole moment of this dipole, induced dipole. So that you have to calculate. So let me give some hint for that. So again, you can find out this dipole moment in two ways. One, you can simply write the standard definitions of dipole moment. P is equals to, in this case, we have a continuous surface charge density into surface charge density. So we can write r vector sigma ds. What is this r vector? So in this case, we have a conducting sphere, and we have noticed that there will be a surface charge density. Let's say this is z axis. So what we have to do, we can consider elementary area here, and in spherical polar coordinate, we write elementary area r square sine theta d theta d phi, and this distance from this this will be our r vector. This will be our r vector. So r vector here, r vector you can write as a capital R into r cap. So if you put them together and then if you integrate all over the surface with respect to theta and phi, you will get the dipole moment. Will get the dipole moment. But if you see that sigma, we have calculated here induced surface charge density sigma, it's a function of theta, and also we have to calculate with respect to theta and phi. So this integration is this sigma will be function of theta. So because of that, this we cannot take this r cap as a constant vector, because when we will change this theta, r cap directions of r cap will also change. So for that you have to write this r cap. If you using this definition to calculate the dipole moment, you have to write this r cap in terms of theta and phi. So what will be this r cap in terms of theta and phi? It will be sine theta cos phi I cap plus sine theta sine phi j cap plus cos theta k cap. So this will be r cap. So once you put everything here, and then if you integrate over the whole surface 0 to pi for theta limit and 0 to 2 pi for phi limit, you will get the dipole moment. So that is one way to calculate this induced dipole moment, because you know the sigma. So using this definition you can calculate. One can also calculate this dipole moment simply using the definitions of potential associated with the dipole. What is that potential? Let's say we have a dipole of dipole moment P, and if we want to calculate potential at a distance r from the dipole, which is if this r is make an angle theta with this dipole moment, then we can write this potential at this point because of this dipole moment. V is equals to 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught P dot r vector divided by r cube. R vector divided by r cube. So we write this in terms of theta. So what we'll get? We'll get P cos theta divided by 4 pi epsilon naught r square. So again, since in this case also you can see that we are, when you're placing this conducting sphere, we are not adding charge, external charge. So total induced charge will be 0. And this potential term is represented here, that this potential is varies with respect to r is 1 by r square. So according to concept of multiple expansion, we can say that the induced charge will be applied as a dipole. And so if you want to calculate this dipole, so you can compare this potential term with this potential. So from there you can also get this P, magnitude of induced dipole moment, and from the figure you can get idea that what will be the direction of this induced dipole moment. So we always take this directions of dipole moment from negative charge to positive charge. So from this figure you can get idea which directions will this dipole moment will be. So using the both definitions, if you calculate dipole moment with using this definitions or this definition, both the cases you will get the same result. So write your answer in the comment box. And also I will request to everyone, so do one exercise, small exercise. So here to calculate this sigma, we have calculated only r component on the surface of the conducting sphere, because we know the electric field will be normal to the surface. So if electric field is normal to the surface, then tangent component, what will be the tangent component? Is 0 or non-zero? So just check it. So for check, what you have to do, you have to calculate theta component at the surface of the conducting sphere. So how we calculate theta component? We can, using this definition, 1 by minus 1 by r. Now we have to take partial differentiation with respect to theta, and then finally you will have to put r equals to capital R. Okay, so do this exercise and also write the answer of this exercise in the comment box. So you have to write two answers in the comment box. One is what will be the induced dipole moment, either you will get one of this option, and second you have to calculate this theta component of the electric field at the surface of the conducting sphere. To calculate this, you'll be able to understand what will be the, you will get the result about the tangent component of electric field on the surface of the conductor. You know already what will be the answer. Without any mathematics you can write that, but after mathematics you can confirm that okay, what we know from the 12th class, it is true. Okay, so write both the answer in the comment box, and I hope you have understood these questions how I have solved. And if this type of questions is asked in exam, I hope you will be able to understand, you will be able to solve this problem also. So using this result, I will also going to solve another problem after these questions. Till then, bye bye, take care, see you in the next video.